All right, today we're going to talk about balanced binary search trees. So the algorithms of the binary search tree work best, that is, they're log n algorithms, when the tree is mostly balanced. Okay, so here's an example of a tree that's perfectly balanced. Right? Every non-leaf has exactly 2 children. Okay. Let's compare this with an unbalanced tree. So this is a tree that has exactly the same data in it, but because of the way things were inserted, the tree happened to look like this. So if you were to insert all these items in exact ascending order, for example, this is what your tree would look like. Here, the tree only looks like this because of the order that we inserted things. And you can refer back to the insertion algorithm to convince yourself that that's true. To search a balanced tree, it takes, like I said, it's a log n algorithm. So to search a balanced tree, there's about log n comparisons to either find the item or discover the item isn't there. Okay, so let's look at the balanced tree here. If we wanted to search for the value 300, for example, well, we know we could tell right now 300 is not in there, but how much work would it take us to find that out? Well, if you recall from our past talks about trees, we would start at the root and say, is that the value 300? No. 300 is greater, so we'd go right. We'd say, is that 300? No. We'd go to the right. Is that 300? No. Is that 300? No. And then we got to a null pointer. That's when we'd stop. So we would have checked basically these 4 different values and found out that the value 300 is not there. Okay, so what is the log of, there are 15 items in this tree? Well, it's about 4. Okay, so that makes sense. 2 to what power is equal to about 15? Well, it's about 4. So it took us about 4 operations to find that 300 wasn't there. However, on an unbalanced tree, right, the tree we have over here, if we look for 300, right, we're going to start here and move down here, and obviously it's going to take n comparisons to find out that the value 300 isn't there. Okay, so if we have a mostly balanced tree, our algorithms are on the order of log n for just about everything. Okay, but this requires that we have at least a partially balanced tree. Okay, if we don't have that like we have here, then our algorithms degrade to about big O of n to do things. Okay, and obviously we want that log n behavior. So let's talk about balanced trees. A tree is considered balanced if the difference between the heights of a node's children is either -1, 0, or +1. Okay, so by what I mean by that, let's look at some balanced trees first, and let's compare the heights. So here, for this top node, if we look at its children, the height of the children in the left subtree is 1, and the height of the right subtree, that's also 1. These leaf nodes, of course, they have a height of 0. There are no nodes below it. And if you take the difference between these two, 1 minus 1 is 0. That means this is a balanced tree. Let's look at another balanced one. This one is also balanced. So here, the left subtree has a height of 1. The right subtree has a height of 2. 2 minus 1 is 1, so we still consider this a balanced tree. And of course, we could check to see if this is balanced too, and it looks like 1 minus 0 is 1. That's balanced. 0 minus 0 is 0. So as long as we're in this range of either -1, 0, or 1, for the difference between the heights of any node's children, we say the tree is balanced. Here's another tree that's balanced. Here we have a height of 2. 2 minus 2 is 0. 1 minus 1 is 0. 0 minus 0 is 0. Okay, all of these are balanced here. 1 minus 0 is 1. That's okay. This guy's still balanced. Okay, all those are examples of balanced trees. Now let's look at maybe some unbalanced trees. Okay, and again, the height of the left subtree is 2 here, and the height of the right one is 0. 2 minus 0 is 2. That tells me that this is an unbalanced tree. However, the subtree, this part of it down here, that is balanced, but as soon as we get to this point here, we could see this is not a balanced tree. Similarly here, we have, again, a 2 minus 0 would tell us that this is an unbalanced tree. The shape is a little bit different, but again, at the topmost element, we have an unbalanced tree. And here's a slightly larger unbalanced tree. Say 4 minus 3 is 1, that's fine. It's not unbalanced here. But if we look at, let's see here, 2 minus 0 is 2. So that says this is unbalanced. This is fine, this is fine. 3 minus 0, that's an unbalanced node. 2 minus 0, that's an unbalanced node. Okay, that one looks fine, and that one looks fine. So here there are 3 nodes that make this tree unbalanced. Now to make a binary search tree balanced, this is something we want to do because we'll get better performance of our algorithms. We're going to check every single time we either insert or delete whether any part of the tree is unbalanced as a result of the operation. If we do an insert and we make the tree unbalanced, we are going to balance it by moving some nodes around. And we would never have a tree like this, actually, because we have 3 different unbalanced nodes. As soon as we had the first unbalanced node, we'd move things around. So we're actually never going to balance anything like this. This has too many unbalanced nodes already. Okay, so let's talk about this process of balancing. In order to balance the tree, we need to know what side needs balancing. So let's look at a few situations here. Let's say we're going to have this this tree that we're going to insert the values 25, 10, and 5. Okay, so if we insert it in this order, the 25 would go here. The next insert of 10, well, 10 is less than 25, so it would go to the left. And then when we insert 5, starting at the root, 5 is less than 25, 5 is less than 10. Okay. But this is an unbalanced tree. It's actually unbalanced here at the top because there are 2 children on the left, 0 children on the right, and that's an imbalance. In order to balance this, right, if we were going to go through this balance operation, our resulting tree would look like this, with 10 at the root, 5, and a 25. Okay, so that's our goal, is to take something that looks like this and turn it into this. This is now a balanced tree. Okay, let's look at another situation here. Let's insert in this order. So we insert 5. Then we insert 10. 10 is greater than 5. And when we insert 25, that's greater than 5. It's greater than 10. So the 25 would go there. And of course, to balance this, we would have exactly the same tree as before. Right, so when I talk about balancing, we have to move some nodes around, but we still have to maintain the relationships that everything to the left of a node is less than or equal to that value, and anything to the right is greater than that value. Okay, there are a couple more situations we have to worry about. Let's say we inserted 25, and then 5, and then when we insert 10, 10 is less than 25, 10 is greater than 5. So we'd have a tree that looks like this, and of course to balance it, we would have something that looks like that. Okay. And then the last scenario, we have insert the value 5. Insert 25 is greater than 5, so it would go here. Inserting 10, 10 is greater than 5, but is less than 25. Okay. And again, to balance, put the 10 there, 5 there, and the 25 there. Okay, these last two cases are going to be the tricky ones. When we have not a straight line, but a crooked line, like we had there, and also here. It's going to be a lot easier to balance when we have a nice straight line either to the left or to the right. Okay, but we'll talk about that in a second. Okay, and of course, any insert that starts with 10 is going to result in a balanced tree. So I won't even draw that out because those won't need to be balanced. Okay, so the question now is, well, how do we balance a tree? And there's two types of balancing. There's right balancing and left balancing. Okay, so let's go back to the case where we inserted, let's say we did an insert of 5, insert of 10, and an insert of 25. This is going to be a nice, easy example here. So when we do insert 5, that'll go on top. 10 is greater than 5, that'll go here. And 25 is greater than 5, it's greater than 10, it would land here. Okay, and as we did that insert of the value 25, so remember we're kind of crawling our way down here, but then we're going to go on the way, we're going to go back up, right? Each one of these resulted in a function call. We're going to return from those functions, so on the way back what we can do is we can check to see, well, is this part of the tree balanced? So here we have a height of 0 and 0, that one's balanced. Here we have a height of 1 and 0, that's within our balanced range. But here we have a height of 2 on the right and 0 on the left, and that makes this guy unbalanced. Okay, so what are we going to do here? We have to turn this tree into the one that has 10 at the center. Okay, and the basic idea is we're going to take the middle node. In this case, it's the node with 10, and that's going to be the new root of the subtree. Okay, the middle node's left, which in this case is null, but that's not always going to be true. There are going to be times when there are some things over here. We're going to store that because eventually we're going to assign it to the top node's right pointer. Okay, so this is going to be the new root is going to be the 10. Whatever's over here, whatever's to the new root's left, we're going to store. Okay. And like I said, eventually this guy's right, the top one's right, is going to point to whatever's over here. Now in this case it's kind of artificial because there's just a null pointer, but like I said, that's not always going to be the case. Okay, then we're going to take the middle nodes, the node with the value 10, we're going to make its left, instead of point to null, we're going to have it point to the node with 5. And then we're going to take the top node's right, the node that has the 5 here, and we're going to make its right the old, or the middle's old left. Okay, so let me kind of draw that out again. So we said 10 is going to be the new root, and we're going to kind of keep track of what's over here to to the new roots left. Right now there doesn't happen to be anything there, but there could be. Okay, next we're going to take the middle node's left, and it's going to point to, instead of whatever it's pointing to here, we're going to make it point to the node with the 5 in there. Okay. 10's right already points to 25. And then we're going to take, again, this guy's right is going to point to whatever was here. So I'll just draw it like that. Okay, and if I draw this a little nicer here, we'd have 10 at the middle, points to 25 on the right, and 10's left now points to 5. And 5's right is going to be whatever 10's left was pointing to before. Okay, so let's go over the algorithm here step by step. So we are first going to mark the unbalanced node as what I'm calling the current node, that I'll use pcur as the pointer. We're going to mark pcurrent's right as the new root of the subtree. We're going to copy the new root's left pointer, because we're going to write over it in the next step. We're going to set the new root's left to point to pcurrent. We're going to set pcurrent's right to be the new root's left, its old value. And then finally we'll set pcurrent to point to the new root. Okay, so just looking at that, that's very confusing. Let me draw a picture, okay, to show you exactly what's going to happen here. Okay, so let's imagine we want to insert the value 150. Okay, so imagine we have this tree as it is here, and we want to insert the value 150. Well, what are we going to do? We're going to start at the root, and 150 is greater than 50, it's greater than 100, greater than 125, it's greater than 130. Here we have a null pointer, so this is for sure where the new item is going to go. Okay. And then, of course, we're going to climb our way back up the call stack, because these were all recursive calls. On the way back up, that's when we have to check, well, are all of our nodes balanced? So this one's balanced because it's brand new. This one's balanced. It has a height of 1 over here and a 0 over there. This one's balanced. 2 over here and 1 over there. 2 minus 1 is 1. Let's see, the height over here we have 3. And on the left side we have a height of 2. 3 minus 2 is 1. That's balanced. But over here we have a height of 1, 2, 3, 4 on the right. And 1, 2 on the left. So this is our unbalanced node. Okay. So what that says, first step is to mark the unbalanced node as pcurrent. Okay, so this guy points here. Okay, step 2 says we're going to mark pcurrent's right as the new root of the subtree. So whatever pcurrent's right, that's going to be the new root. So pcurrent points to this node. That means the value 100, that's going to be the new root. That's step 2. Step 3 says we're going to copy the new root's left pointer. So new root is here. Its left pointer refers to this whole subtree. So I'm going to create this pointer called temp. And temp is going to be a node pointer that points to the new root's left. Okay. So copy the new root's left pointer. Okay. Step 4 says we're going to set the new root's left pointer to be pcurrent. That means the new root's left right now points here. We don't want it to point there anymore. We want it to point here. Okay. That's step 4. Setting the new root's left to be pcurrent. Okay, and lastly, step 5 is we're going to set pcurrent's right, okay, which right now pcurrent is here. Pcurrent's right points to 100. Okay, we want to move this value so it doesn't point here, but it points to this value here, the one we copied over. Right? So it was the node with 100, its left pointed to 75, and 75 was this whole portion of a subtree. Now we're going to make pcurrent's right point to that one. That was the fifth step. Okay, and lastly, we're going to set pcurrent to point to the new root. That's mostly because we're passing by reference. Okay, so that when the function call returns, the passed in pointer actually got updated. Okay, so this is probably this is pretty ugly. Remember, this fifth step was to make pcurrent's right point to this temporary one. Let me clean this up. Let me straighten this out and show you what happened. Okay, so this is our new tree. We have, remember, 100 was going to be the new root. Its right is 125. Its left was 50, and 50's right pointed to 75. Okay, so let's take a look at that again. 100's right was 125. We changed 100's left to point to the one with 50. Right? And remember, 50's left, that's unchanged, but 50's right now points to the 75. Okay, and what we're left with now is a balanced tree. If we march through here again and count, we'll see that this is perfectly balanced. And we still have the relationships right, meaning everything to the left of 100 is less than or equal to 100. Everything to the right of 100 is greater than that. And that's true of all these nodes. Okay, and that's of course is critical. Okay, so let's think about, well, what about the other unbalanced tree? We saw the kind of the straight line scenario. Let's say we did this. Say we had an insert of 5, then 25, then 10. And this is what I call the crooked scenario. Because when we did the insert of 5, we'd have that. 25 is greater than 5. We'd have that. When we insert 10, 10 is greater than 5, but less than 25. Okay, so let's apply the exact same algorithm on the crooked unbalanced tree. And let's see, let's go back here. So we're going to mark the unbalanced node as the current. We are going to take pcurrent's right and mark that as the new root. Okay, we're going to copy the new root's left pointer. We're going to store that in temp. So new root's left is this one here. Temp is going to point to the value with 10. We're going to set the new root's left pointer to be pcurrent. So instead of this guy pointing here, it's going to point there. And we're going to set pcurrent's right to be the new root's old left. So this guy, instead of pointing here, he's going to point to temp. Okay, so let me straighten this out here, and that will make 25 be on top. Let's see here. Then 25's left is going to point to 5. And 5's right is going to now point to 10. Okay, and you'll see, right? This tree isn't balanced. It's not the we don't have 10 at the center anymore. So now, in fact, it's unbalanced on the other side. It's unbalanced on the left. So applying this algorithm to one of these crooked scenarios always gives us the other one. Okay, so we're going to have to do something about this. The algorithm works only when we have those straight line scenarios. Okay, if you attempt to balance a tree on the right using the algorithm that I just talked about, and it's not balanced afterwards, okay, we're going to have to handle this as a special case. Okay, so let's look at some code here. This code will be inside your insert function, your recursive insert helper, or I'm just assuming it's called insert. So recall, of course, we check to see if we have a null pointer. If not, we check to see is the value greater than what we're looking for. If so, we move right. That's where we are right here. This says this is the recursive move to the right, and eventually we're going to insert this piece of data. On the way back, though, on the way up the call stack, okay, we're going to encounter this bit of code. Okay, so we call the recursive insert, and eventually we're going to have a return from that, and the flow of control is going to pick up right here. Okay, so on the way back up, if the tree is not balanced after we've done the insert, okay, well then what we're going to do is we're going to balance to the right. We know it must have been, the new item must have gone on the right because that's the direction that we moved when we called insert. So this those 5 or 6 operations that I talked about, those are going to happen inside the balance right method, and P is the pointer that I think actually this would be something like this. So P is the pointer to the node that gets passed along through this recursive call. Okay, so basically we check to see is the tree balanced. If not, we balance to the right. If it's still not balanced, then we have one of those situations where we have the oddly shaped tree that got turned into the other type of oddly shaped tree. And the solution to this seems a little awkward, but what we're going to do is we're going to take P's left and we're going to balance it to the right, and then that's going to make a nice straight line tree, which we will then balance to the left. Okay, so let me kind of draw a picture that goes along with this. Okay, so remember we started out with this tree. Five, 25, and 10. And I'm saying P is pointing to this one here. If we call balance right, okay, we just looked at what's going to happen. We're going to have 25, 5, and 10. Okay, so after we do that, we check, well, is the tree balanced at this point? Right? P, because we passed P by reference, P is going to be updated to point to this one. The tree is still not balanced, so what we're going to do is we're going to take P's left. We're going to go down here, and we're going to call the balance right function. And basically what that's going to do is, since we're going down a level and we're balancing from here, okay, that's going to, again, make 10 is going to be the new root. And this one's left is going to be 5. And now we have this nice straight line scenario. Okay, but now we're unbalanced to the left. So when we call balance left, this should, of course, transform into what we were looking for originally, where we have 10 at the center and 5 and 25 hanging off of it. Okay, so it's kind of an odd process that we go through, but this is the classic balanced tree algorithm. So we check to see if we have an unbalanced tree, which we did. We balance it to the right. If we're still unbalanced, we're going to balance this part of the tree to the right. That's going to turn the tree into the straight line scenario. And then we balance left to get here. Okay, the algorithm, we talked about the right. The algorithm is very similar for left-hand balancing. Basically, you'll reverse all left and right references. Okay, and this type of tree is called an AVL tree. It's named after the inventors who came up with this in the early 60s. Okay, so this is a pretty standard data structure. It's been around for quite a while. One thing we haven't really talked about is, well, how do we calculate these heights? So should we store the height of the tree in each node? That's actually what I'm going to suggest that you do. So we have a node, it has some data, it has a left and a right. Okay, and one thing we can do is we can have a height variable for the left and right subtree. Okay, and anytime you insert, you would need to know if the height has changed, and you might also want to change the height as you move back up the recursive call stack. So I'll leave that as an exercise for you guys. Also keep in mind when you delete, that also might affect the height. Okay, and that's our balanced binary search tree. If we have a truly balanced tree, right, what this data structure does is every time we insert or delete, it makes sure the tree stays balanced. Then we have the benefit whenever we want to do a search, we know for sure it's going to be a big O of log n operation.